All right, welcome back, Calc AB students. So we're going to be continuing our coverage of section 4.4, applications of definite integrals. The next thing we want to do is look at what are called accumulation functions, and we'll see why they're called accumulation functions a little bit later. But first, let's set like kind of a context of what we're doing here. Okay, so let's say I have a xy axis, and let's say I have a function that's a derivative. So this is f prime of x. Okay, so we can we know from before that if we want to graph a possible f of x, well, here are my critical points. So I've got a critical point here and here, and this is minus to plus and plus to minus. So the one on the left is a relative min, the one on the right is a relative max, and then up here I've got an inflection point, and so I know that this is a possible curve. Oops, I gotta make sure these line up. But this is a possible curve of f of x. But there's really let me make sure these inflection points and critical points line up. But remember, there's really an infinite number of solutions here for f of x, because f of x is the antiderivative of f prime of x. However, so I can get a better eraser going here. However, if I know a particular solution, so let's kind of redraw this thing. So let's say I have a known point, and this is all stuff we've done before, but something new is coming up. Okay, so here here is my f prime of x, and let's say I have a known point on the graph of f of x, and so let's say, just for sake of argument, that let me draw a solution. So let's say this is f of x, and this is my known point. So I know that this is my solution. Okay, so one of the things we couldn't do before is, if I just have f prime of x, is to figure out what all these other points are, just graphically. And this is important to note that this is graphical. And so I know f of x is this distance from the x-axis up to the function. But I want to find the exact values of this. Okay, so what I'm going to do is I'm going to start off with that the first fundamental theorem of calculus. And what I'm going to do here is I'm going to have the form that we were looking at just in the last video. So I got f of b is equal to f of a plus the integral from a to b of f prime of x dx. Okay, so now this is what's new here, is I want this b to be a variable, so that I can solve for f of x, and that's, so if I go back to that graph, and then here's my f of x, I want to be able to solve for any point on this curve, given my f prime of x. Okay, so I'm going to make b my variable, and then a is my known point. So if I go over here, then this b is also going to be a variable. And I want that variable to be equal to x in both cases. Okay, so what I'm going to do is I'm going to just change b to x. So I've got f of x is equal to f of a, plus now my integral goes from a to x. But the only problem here is that if I make this b and x a variable, then I've got these x's here. And because this can lead to confusion between this x and this x, generally what happens with these accumulation functions is I need like a dummy variable, if you will, that's not x, just kind of as a placeholder until I've completed the integration process. And so traditionally that dummy variable is t. Now t is not necessarily time, it's just a dummy variable. So I'm going to write this as I'm going to write this as f prime of t dt. And the whole point of doing this is so that this x and this t are technically different variables to start off with, so I don't confuse the two. But this is really going to become a function of x once I complete the integration. And so this thing here is what's called an accumulation function, which is just the first fundamental theorem of calculus where b is a variable. Okay, so let's do it with this. And these are the types of problems that show up on the AP exam all the time. So for an example, let's go ahead and I'm going to draw this out. And this particular equation is very, very useful when you have the graph of a function, but you don't, or the graph of the derivative, but you don't necessarily know what the function is. Okay, so here I'm actually do this in a different color. Okay, so here is a graph. Okay, and let's say that this graph is the derivative f prime, and I'm going to put that dummy variable in t. And I know, it's known, that f of x, and now here using this f kind of can become a little bit confusing, so I'm going to make this g of x. So it's known that g of 3 is equal to 7, and that g prime of x is equal to f prime of t. And this isn't exactly true, and we'll fix this later, but I just want to kind of show you that this f prime is really g prime. So this is really the graph of g prime of x. This isn't technically correct, but we'll deal with it later. Okay, so now if I were just to give you a graph of the derivative, which I've done before many times, you know that I've got critical points here, 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 and here, and this is actually supposed to be at 0. I know that this critical point here, it's going from negative to positive because this is the derivative of the function. So the original function, g of x in this case, is going to have, if I'm going, so the function's decreasing and then increasing, so that's a relative min. I've got a relative max here, relative min, relative max. I've got an inflection point here, here, and here. It's concave. I'm looking at the slope of the derivative, so it's concave up until this inflection point, then concave down to this inflection point, concave up to this inflection point, and then concave down. And that's the original function, not the derivative. Oftentimes on the AP exam, they'll give you something like this, and then they'll ask questions about extrema, inflection points, and concavity, and we've already done all of that. But the new thing is dealing with these accumulation functions. Okay, so let's put in some areas in here, and if it was known shapes like semicircles or square or lines, or you just break up into rectangles, triangles, squares, and semicircles. But in this case, I'm just going to go ahead and give you the area so we can concentrate on the concepts here. So the area of this section, the magnitude of the area is 3, magnitude of the area is 2, magnitude of the area is 4. Okay, so we want to do something new now. And so I want to find, first I want to find g of 5. Okay, so what I'm going to do is I'm going to use the equation g of x in this case. So g of x is going to be equal to g of a plus the integral from a to x of f prime of t dt. Okay, so I'm going to put my numbers in. So g of x is going to be equal to g of a, and g of a is going to be whatever my known point is. So a is 3, so be careful. This a is 3, because that's the given value. So this is going to be g of 3 plus the integral from 3 to x of f prime of t dt. Okay, so if I'm finding g of 5, then what I'm going to do is I'm going to put my x value, in this case, is 5. So I can use this general equation, and I'm going to write g of 5 is equal to, well, this is always going to be consistent. This g of 3 is my given value, so that's 7. So it's going to be g of 3, which is 7, plus the integral from 3 to x, and x in this case is 5, of f prime of t dt. And this integral right here, this definite integral, I can find by looking at the area, because this is the integral of f prime of t, so this is going to be the area bound between 3 and 5. And I should put some x values on here. So let's say this is x equals minus 3, x equals 0, x equals 3, and x equals 5. Okay, so if the integral is from 3 to 5, then it's going to be this area in here, which is 4. So this g of 5 is going to be equal to 7 plus the area represented by this definite integral, which is 4. So therefore, g of 5 is equal to 11. And what this tells me is that I know that on the graph of g, the original graph, because the graph that's shown is the derivative, on the original graph, the y value at x equals 5 is 11. Okay, let's find another value. And I can actually find, in this case, I could find any of these points that I have listed. But I want to find g of minus 3. Now be careful here. So if I look at the accumulation function, I've got g of x is equal to g of 3 plus the integral from 3 to x of f prime of t dx. And in this particular case, my x value is minus 3. So I want this x value to be minus 3, which means I want this x value to be minus 3. And I know that g3 is 7. So I've got g of minus 3, because I'm going to change all my x's to minus 3, is equal to g of 3. Well, g of 3 was given to be 7, plus the integral from 3 to x, but x in this case is minus 3, of f of t dt. Now notice here that it's going from 3 to minus 3, so I'm going to rewrite this as 7 plus, and actually I'm going to make this minus, so that's because I'm flipping the integral, or I'm going to flip the integral, so that's going to be 7 minus the integral from minus 3 to 3 of f prime of t dt. Now if I go up to my graph up here, minus 3 to 3, just this integral, and we'll deal with that minus sign in a moment, but just this integral is going to be equal to the integral from minus 3 to 0, which is positive 3, plus the integral from 0 to 3, which is minus 2. So I'm going to go ahead and put that in. So this is equal to 7 minus the area 3 plus the area minus 2. And that's a minus 2 because it's below the x-axis. So 3 plus a minus 2 is 1, and 7 minus 1 is 6. So that tells me that g of minus 3 is equal to 6. And I can do this for any point. And so sometimes they'll actually ask you, okay, what's the point of the extrema? Well, we can do that now, because I know, let's say they ask you, what's the point of your absolute mins? Okay, well, I know that here, this is the graph of f of prime, which is g of prime. So I know that here I've got a relative min at x equals minus 3. But now I can actually find out what the y value is if they're asking for the points. And that y value is g of minus 3, which I found through this process to be 6. And my other minimum occurs at x equals 3, well, that's a given point. So if you're asked that question, it's kind of cool because now you know the answer. So the points relative mins are going to be xy is equal to, the first one is 3 comma 7, which is given, and the second one we just found is minus 3 comma 6. So now you can actually find the y values for these types of problems, which is pretty cool. All right, next. Now the reason that these things are called accumulation functions is that the solutions accumulate as you keep kind of marching forward. So let's say I have some function, and I'm just going to kind of draw it like this. So here's my function of x. All right, and let's say I have this function of x actually is, I want it to be a derivative. So I'm going to make this equal to f prime of t, because that's my dummy variable. Let's say I know that g of 0 is equal to 8, for example, and I want to come up with the accumulation function. So I know that g of x would be equal to g of 0, because a is always your given x value. So that's g of 0. So that's g of 0 plus the integral from a, which is your known value, to x of f prime of t dt. And so, so here I've got g of x is equal to 8 plus the integral from 0 to x of f prime of t dt. Okay, so let's say I wanted to find g of 1. Well, if I wanted to find g of 1, then I have 8 plus the integral from 0 to 1 of f prime of t dt. And so that would just be 8 plus this area here. So 8 plus this area here. And if I wanted to find x of, or g of 2, then it would be 8 plus then this whole area. If I want to find g of 3, then it would be 8 plus this whole area from 0 to 3. And so as you can kind of see, the function, this piece accumulates as I keep marching forward. And that's why it's called an accumulation. Okay, and the last thing we're going to cover today, and I'll make another video tomorrow on the net change theorem, which is actually the last thing we need to cover in 4.1. But the next thing we need to cover is, we're at the 17-minute mark. I'm going to make one more video this evening on the second fundamental theorem of calculus. So I'm going to come right back.